Hello everyone. Today let's talk about multivariate linear regression. In the earlier video we have seen linear regression with single variable. If you have multiple variables, we call it multivariate linear regression. And we have seen an algorithm gradient descent to solve the linear regression as well as multivariate linear regression. We will also see one more method to solve the linear regression. Earlier we had a single variable, size of the house, determining the price of the house. Now we have more variables. We have age of the house as well as number of bedrooms, determining the price of the house. Now to represent this in a linear regression hypothesis format, we have theta 0 plus theta 1 times size of the house, theta 2 times age of the house, and theta 3 times number of bedrooms. And the goal of this multivariate linear regression is the same, to solve for the parameters theta 0 till theta 3. So this is the hypothesis for a multivariate linear regression. Let's move on. And we also see, okay, let me just move my video this side. Okay. There is one more type of problem called polynomial regression. So linear regression, we have variables to the power of 0 or 1. At max it will be x. For polynomial regression, the power of the variable will be 2 or more. So if we have at least one variable which has a power 2 or more in the hypothesis equation, we call it a polynomial regression problem. So let's see. Earlier we have the hypothesis represented in this manner. And since this is a linear equation, what we can fit at max is a straight line. So given a problem like this, where size of the house is determining the price of the house, what we can draw at max is a straight line that can fit our data well. Sorry for the jumble, but yeah, assume this is a straight line. Now, if you want to fit a curve that can fit the data much better, then you can go for a quadratic equation, which is the variable to the power of 2. So we can have one more variable called size square. So we can have our hypothesis represented like this in a curve format. Now, even this may not be sufficient because a quadratic equation, if we go further, it might go down like this. We don't want that because as size of the house increases, we want the price of the house to go up. Then we can fit a cubic equation to a problem. And also, since we have only one variable size, we can determine that and put size cube to it. Now we can have a nice equation like this. So we can see, in effect, we have to solve a polynomial regression problem to solve for our hypothesis and to get the parameters theta 0 till theta n, which can minimize the cost function. But you can see, usually we don't do that. We don't solve polynomial regression problem. But instead what we do is, whatever the polynomial type variables are there, say size square or size cube, we name them as new variables, and we ultimately represent it in the form of linear regression, sorry, a linear equation, and then solve for the linear equation. Okay, let me put my video this side. Okay, sorry for the interruption. So given our hypothesis like this, what we can do is we can put size we can put as x, and size cube will become x square x cube. Now we can put x square as another variable x2, x cube is another variable x3, and now our hypothesis looks just like a normal linear equation which can be solved using a linear regression. So this is how we solve the polynomial regression type equations as well. So it need not be like we always have to put a straight line there. We can put different polynomial equations as well that can fit our data much better. But to solve those problems, we can convert those polynomial equations to normal equation and then use the linear regression methods to solve it. Let's move on. So there is one more method other than gradient descent for solving linear regression, that is normal equation method. So this method is used when we have a small number of features or small training data. And this is much quicker compared to gradient descent because there is only one iteration required for this. You will see that in the later slide. And it will give much accurate result compared to gradient descent. It will reach the global optimum quickly. Now, when do we not use the normal equation method? We don't use the normal equation method when we have a large set of training data and we have a large number of variables. That time, we don't use the normal equation method. Usually in classification problems in machine learning, like image classification or similar problems, we use gradient descent. We prefer gradient descent due to the large number of variables involved. Okay, so let's see what this normal equation method is. So our earlier equation, let's represent in this manner, where x0 is 1. Then you can see it just looks like our linear regression equation that we have seen previously. Now representing them, okay. Now the cost function j of theta is the mean square error in the test data. So we are subtracting the hypothesis from the test data, test result, and we are taking the square of it and we are taking the mean of it. So it's a mean square error cost function. So given the hypothesis and the cost function in this manner, to minimize j of theta, what we need to do is we need to take a derivative of j with respect to the parameter and equate it with 0. For example, to derive theta 0, we need to take d of j by d of theta 0, keeping other parameters as constant, and then solve it for 0. You will get theta 0. Similar way, to solve for theta 1, you need to take d of j by d of theta 1 equal to 0 and solve theta 1. This way we get all the parameters starting from theta 0 till theta n, where n is the number of variables we have. And if we derive this equation, we will come to know that the cost function will be minimum when these parameters are derived in this manner. And there is a simple formula as well to solve this normal equation. So given the parameters and variables in the hypothesis in this manner, you can feed all the variables in the test data to the x, and all the variables, all the results to y. And then from this test data, we can get the parameters theta 0 till theta n. using this manner, where theta represents the parameters theta 0 till theta n. We need to take x transpose multiplied with x. So these are matrix multiplications, and take the inverse for it, dot, again x transpose and multiply with y. So this y is nothing but this y only. So this way, in normal equation method, we can get the accurate result. As you can see, this is a single step process. That's why it is much faster compared to gradient descent. And since taking the inverse is costlier, which is on the order of bigger of n cube, that's the reason only when you have small set of variables and small test data, we prefer normal equation method. And you can argue like some matrices doesn't have inverse and all. That's okay, because so we take usually pseudo inverse just to overcome that. And if you know Octave programming language, this is just a single line of code to solve for theta. So P is nothing but pseudo inverse x apostrophe, you can see this is x transpose multiplied with x close, and this is multiplied by x transpose multiplied by y. So I'm sorry, here I mentioned it's a dot, but it's not a dot multiplication, but it's a normal usual matrix multiplication. So the single line of code will help us get the theta. Okay. Thanks for watching the video. Bye.